This work, pattern recognition in agricultural soils using microwave interdigitated sensors on polyimide and PTFE substrates assisted by machine learning, presents an innovative approach for soil characterization using advanced electromagnetic technologies and multivariate statistical analysis. Agricultural soil samples were collected at the El Potrillo Ranch in Chihuahua, Mexico, at different depths, surface, 30, 60, and 90 centimeters. These samples were compared with reference solutions including distilled water, deionized water, and commercial glyphosate at 1% and 5%. For this study, interdigitated sensors were designed on flexible polyimide substrates using laser photolithography. Configurations were created with 3, 6, 9, and 12 comb-type electrodes. The electrode geometry was designed using CAD software CLEWin and SolidWorks. Polyimide substrates with a dielectric constant of 3.2 from DuPont were used. PTFE substrates from Rogers Corporation with a dielectric constant of 2 were used for comparison. Each substrate was coated with 4 milliliters of positive photoresist. Exposure of interdigitated patterns was done using the MicroWriter ML3 laser lithography system with a 2 micrometers laser beam at 365 nanometers wavelength and 60 mJ/cm superscript 2. Exposed areas were developed in all-resist developer and etched in ferric chloride for 20 minutes. SMA connectors were soldered for high-frequency testing. Results: microwave interdigitated sensor geometry involves several parameters: dielectric constant, number of digits, width and gap between digits, bar spacing, and digit length. Thevenin's maximum power transfer theorem was applied to ensure impedance matching at 50 ohms. COMSOL multiphysics simulations evaluated how geometry affects impedance. Each added digit acts as a parallel capacitor, increasing total capacitance and lowering overall impedance. Figure 4 showed impedance changes as digit width varied. Figure 5 demonstrated maximum electric field strength when the digit width was 0.5 millimeters. Figure 6 showed peak field intensity on the PTFE substrate, air equals 2.0, confirming that lower permittivity improves field strength and detection. Figure 7. Electromagnetic characterization was done using a vector network analyzer, VNA, measuring the S11 reflection parameter every 60 seconds for 50 minutes. This helped assess substrate sensitivity to analytes dissolved in water. Data was analyzed using machine learning algorithms. Figure 8. Show characterization of sensors. Figure 9. Principal component analysis, PCA, reduced data complexity and identified key patterns. The first two principal components explained over 99% of the sample variability. There was a strong correlation between deeper soil samples and diluted glyphosate solutions, indicating higher herbicide absorption at depth. Surface samples showed greater similarity to distilled water, indicating less contaminant retention due to volatilization and degradation. There was also an interesting correlation between soil samples and water from Bustillos Lagoon, suggesting possible interactions between agricultural soils and surface water sources. In conclusion, this study demonstrates the feasibility of combining microwave sensors with statistical techniques for pattern recognition in agricultural soils. This method optimizes sensor design and provides a powerful tool for environmental monitoring and precision agriculture.